All right, so we're perfectly on time. So we'll move on to the second talk.
Okay.
So the second talk will be given by Tjonnie Li from the Chinese University of Hong Kong. All right. So the title will be Gravitational Lensing of Gravitational Waves.
Yes.
Let's welcome Tjonnie.
Thank you everyone. I'm very happy to be here. Thank you very much for the organizers for giving me a chance to talk a little bit about, LIGO. And I think, you guys have heard a lot of different things, but originally I was going to talk about gravitational lensing of gravitational waves. And then I saw the schedule being published and I saw that George has taken an interest and was scheduled 2 talks before me. Then fortunately on Sunday, Alessandra sent me an email saying that she's not going to make it because initially Alessandra was supposed to go first, so I let her take all the boring parts. But so Alessandra couldn't make it and George was before me. So what do? Change the title, and I'm going to talk a little bit more about some of the things that Alessandra was supposed to talk about, but I was convinced by a few colleagues here to say a few words about lensing at the end of my talk. So there's still a few slides there, but I'll start with some of the things that Alessandra couldn't mention. So this is a figure that everyone has seen, I think the 3rd or the 4th time now. So this is just all of the gravitational waves in blue, and this one is the binary neutron star one that we've seen so far in LIGO. And so that's going to be the premise. And based on these detections, I want to discuss several things that have to do with fundamental physics. And the first topic I want to talk about is test of GR. Right? So what can we learn from these events about some of the fundamental aspects of general relativity? Secondly, I want to talk about understanding the nature of compact objects. So these are compact objects that we've seen. There's a lot of postulation that these must be black holes. But one of the things I'd like to show is some of the things that we've measured and what can we learn about whether they are black holes, neutron stars, and so on. And finally, like I said, I'll talk a little bit about cosmology and about lensing as well. Okay, so without further ado, let's start with the first part, and that is test of general relativity. And before I actually show some of the LIGO results, I'd like to make the point that a lot of people say, well, we've done many tests of GR, and GR has passed with flying colors. So what are you testing? What do you do this for? And to convince you that what we do is actually useful, this is actually a figure where here on the x-axis is the time scale, and on the y-axis is the curvature. And you can see some of the past experiments that were done, and this is where LIGO sits. This is the first event, second event. This is where it sits. So even in terms of time scale and curvature, this is really in a different regime than we've been able to probe so far. Or you can flip this around a little, and you can get the potential versus the curvature. And again, even in this view, the gravitational radiation from a binary gives you a unique perspective on the theory of general relativity. Okay, now the question then comes, what do you test for, right? If you've got GR in hand, of course you can then only do maybe a verification. But there's a zoo of alternative theories. Okay, even if you, in the center keep, Lovelock's theorem, in mind, there's still many different directions in which you can, propose, deviations, extra fields, higher dimensions, equivalence principle violations, and so on. And so what do you do? Now, luckily, some of these alternative theories may be mapped to anomalies in GR. So still, just by looking at GR and whether GR holds up, it may give us a hint as to, what are the possible alternative theories. Okay, so what are we working with? So this is a plot that I often show as well, and this is the actual gravitational wave signal that we've seen. And I'm showing a couple of things. So in gray is the signal, is the data. Now in light blue, we see, let's say, the best fitting template. This is GR template. This is our best fit. Now in dark blue, what we do here is we try to reconstruct the gravitational wave strain without assuming, GR, without assuming a template. And instead, we just look at how much cross power is there between the two detectors. And so you can see that the dark blue is a little bit broader than the light blue. So if you will, this is the space you got to, this is your freedom that you got to play with between, the signal being there and whether GR is your correct theory to work with. And so there are many regimes, and Ray talked about this, and then other people have talked about this as well. So in the very early parts, you got so-called in-spiral, and this is the part where we understand, possibly the theory, to the fullest extent. Right? You can use the PN expansion to test, let's say the predictions made by GR. But of course, in here, you also have the assumption that these are black holes or neutron stars. But the question could arise, what if they're not? Right? What if they're, like, say, boson stars, quark stars, and so on? So this is one of the things that we can look for in this regime. Now with the plunge and merger, this is mainly highly dynamical. It's something that's very hard to model theoretically, and we mainly rely on numerical simulations. But nevertheless, we can still use this part to test the consistency within what happened before that. And finally, the ring down, that's the last portion. This is where you could do things like no-hair theorem test, test of the ring down signal itself. This is what was discussed earlier. So this is roughly the setting. Now, arguably the most agnostic thing that you can do is start off with what you think is GR, right? This is what we use a template for, and then just allow for deviations. So suppose you have some parameterized way of writing down the waveform, we can just add an arbitrary deviation to it, a fractional deviation, and then you just go and measure these things, which are supposed to be 0, but if they're non-zero, you may have found something that is not fully GR, or something that you haven't modeled. And you can do that for the in-spiral, maybe the intermediate regime, even all the way down to the merger ring down. But again, it will depend on how much you trust your model itself. Okay, so for the in-spiral, and this is then classified by this so-called PN expansion. So you've got many orders in PN, and this is the result from the first event. And in blue, you can see the limits set on this deviation. So how far is it away from 0 fractionally? And that's what you see in orange. In blue, you see what we could do with the most relativistic binary. And you can tell just by a single measurement, the first detection that we did, we shaved off many orders of magnitude, or things that simply weren't being probed before. And just to highlight, why is this important? Here at 1.5, this is the first order where the nonlinear effects kick in. And already here, there's pretty much no constraint from the binary side. So even just by the first detection, by being able to measure that and compare that with the template, we've put quite stringent bounds on nonlinear effects. And then if you go further, you can get spin-orbit, spin-spin coupling, and so on. So more complex physics that is being tested with this detection. Now, subsequent detections have started to place more stringent bounds, but they're all in the same order, right? So every subsequent detection is just adding increasingly to these constraints. Now we can also look at the last part of the signal, and then just focus on the ring down. Now, in order to just see the ring down, you need a very, very loud signal. And this is the this is the result from the first event, which is arguably the loudest one, but also the heaviest one, so that the majority of the ring down signal is in band. Now here is the quasi-normal mode frequency and the quasi-normal mode decay time. So it does seem that something is decaying, right? But exactly what it is, and with what exact parameters, I think that is still uncertain. So we don't know necessarily much about the ring down. We just know something rang down. The signal stopped at some point. But if we now project to the future, and this is actually this is a figure where you make projections from O1, O2, all the way to advanced LIGO, and then ET, and so on. What can you expect in the future? And so, just by looking at observable ring down signals, this is the number of events per year that you expect. And already in and at around advanced LIGO, there may be a few up to 10 that will have an observable ring down signal. A little bit like what we saw here. But in order to have significant ring down signal, where you can really pin down even just the dominant mode of the ring down, that situation is here in the empty ones. And for that, the message is you may really have to go to third generation detectors before you have enough signal to noise to be able to identify even the dominant mode of the ring down signal. Okay, now you can also, and this is what I mentioned earlier, you can compare the in-spiral part to the kind of merger, post-merger part. And this is what was done here, where you simply chop up the signal in half, roughly equal halves in terms of SNR, signal-to-noise ratio, and you compare, is the first part of the signal consistent with the latter part of the signal? Again, these are some of the low-level tests that we do just to make sure that what we saw is consistent with GR. And as you can see, this is projected onto so-called final mass and final spin. The two things overlap, and there isn't much cause for concern. Okay, now you can also work in a different direction or work differently, and that is you assume a specific alternative model, and then you're gonna see if you can measure or constrain parameters in that model. So this is an example where you put in the dispersion relationship of your gravitational wave, you put in a massive graviton component. Again, this isn't full massive gravity, but this is just in the dispersion, you put in a massive graviton component. So you've got a mass of the graviton or a Compton wavelength, and when you do that, you can then use the existing detections to put constraints on this lambda g. Right? That's another strategy. And so this, you can even go a step further, and you can say, okay, well, what if I let this whole dispersion relationship thing go, not even a specific massive graviton, but instead some generic Lorentz invariance. You can parameterize that with A and alpha, and then you can try to measure or try to constrain alpha. Right? That's another game that you can play. And so in this zoo of theories, I think a lot of things that have been done is, given a specific theory, you take the LIGO, measurement, and what bounds can you put? That's really the game that can be played at the moment. Okay, now you can also look at other aspects of gravitational waves. And so one of the things that I'm showing here is the polarization. So if you believe GR to be true, there are only two polarization states, plus and the cross, right? You can go like this or that. Now, of course, if you take any generic metric theory, then you're no longer constrained to these two polarizations, and you can have others. You can have a breeding mode, that's where the whole space expands and contracts equally, or you can have vector modes, where it's pointed in a particular direction of propagation. And you can then ask the question, what's the ratio of probability? Like, how likely was it that, this was just a GR, so pure tensor, or whether the signal came from a pure scalar. Okay, and so for GW1509, this number is, this is so-called log base factor, so the log of the ratio of the probability is 0, so the probability is just 1. So 1 to 1. So the first event wasn't conclusive. Now, that isn't very strange if you think about it, right? You have 2 LIGO detectors for the first event. Now, the LIGO detectors were built to optimize detection. And so what you want to do when you optimize detection is you want to build the detectors so that they are aligned. Because if they're not aligned, then there are areas in the sky where one detector may see something, but the other doesn't. And so you want to align them. But by aligning them, you also lose out on the polarization information. And so with the first event, of course, we did put a number to this question, but this question itself was very hard to measure just with the LIGO detectors. Now, if you take the first LIGO Virgo detection, the story changes because now you have a third detector. And with that third detector, and especially breaking through this, alignment problem that the 2 LIGOs have, you can suddenly make much stronger statements. So for example, with this 170814, so this was not the BNS detection, but this was the first detection that 3 detectors saw. And that is, you can see that now GR is starting to be favored. So pure tensor mode is favored over pure scalar mode. Or a pure GR for pure tensor mode is favored over a pure vector mode. Now that by itself may not seem very impressive because you can come up with a theory where you have mixed, you have tensor and vector, or even you have the whole range. You have tensor, vector, scalars. Now with 3 detectors, this is as much as we can do, right? Because you need enough number of detectors to break through the degeneracy. And so this is a case for where more detectors come into play. We will be able to have much stronger information about the polarization content of gravitational waves. But so far, tensor doesn't seem to be causing problems. That's the message here. Okay, so now looking a little bit ahead in the future, because we can talk about some of the properties. Early in the conference, we heard also about the speed of gravity, just by looking at the difference between the EM signal that came to us and the gravitational wave signal. And if you chalk all of that up to just some speed difference between gravitational waves and electromagnetic waves, then you can set bounds. Right? Those are kind of the more things on the properties. Now, quite recently, there have been a lot of work done on so-called exotic compact objects and what they may entail. So this is an example where you've got an exotic compact object where the gravitational wave bounces off and it produces so-called echoes. So instead of the top part is the black hole potential, and you can see you just go into 0. But if you have an exotic compact object, you get this cavity over here where you may be able to see echoes from the signal, and that you may be able to detect in order to see whether you may not be dealing with a black hole after all. Now, especially the time scale at which these echoes occur is characteristic to the object you're looking at. So depending on the object, you're going to have a different time scale, and it's related to the size of the object itself. Okay, but of course, if you can detect these echoes, there's a lot more you can learn from the amplitude. How fast does the amplitude decay? The spacing between different echoes, and that you can do. You can measure to learn a lot about the compact object. Now, there's already been claim, not by the collaboration, but there's already been a claim that this has been observed. I don't want to get into too much of the exact detail, but I do refer you to a somewhat critical note to this, that I guess, details a little bit more about some of the shortcomings of the analysis that did claim in the end detection. So the jury is still out, but I think for now, I don't think we need to worry that we've seen echoes or anything, but it's something to keep in mind in the future. Okay, so nature of compact objects. So we've seen binaries going around each other, and everyone immediately goes and says, oh, these are black holes, right? They're so heavy, they must be black holes. Now, of course, that isn't necessarily true, or necessarily the case. And so what we're trying to do here is to relate, microphysics back to the, properties of the object itself. So this is just density versus pressure, and you can convert that into radius versus mass, depending on, what you assume the object to be, right? Neutron stars or more exotic things like, again, boson stars, quark stars, or even fuzzballs and everything. Now, if you have an object that isn't a pure black hole, and we've seen this throughout, then you get some very interesting physics, right? It's no longer just pure GR. You get a lot of, microphysics, nuclear physics, and everything into play. And things will be very different. In particular, what will be different is in the in-spiral part, you'll have this tidal deformability, right? The star will, to a certain extent, deform and extract energy from the gravitational wave, from the orbit itself. And so what you'll see is that, the coalescence happens faster because there will be energy into deforming these systems. Towards the end, you see a complete disruption, and then after the merger, so the post-merger signal looks completely different from what you expect from black holes, right? The black holes ring down very efficiently, whereas, if you have some extended object that, exhibits some post-merger radiation and much more support here at the end. Okay, so the first part, so this is after the first binary neutron star detection, we set out to measure the tidal deformability, so at this stage, and just, how large is the tidal deformability. And so you see here on both sides, you see the tidal deformability for the first object and the second object. And it may be a little bit, okay. So if you go, this is less compact and going to more compact. And you can see here, it's the 68 and 95% confidence interval. And then you see several models being plotted here. Several neutron star models. And so if you were to believe these results, I think, some of the more hard models, neutron star models are, are in trouble, becoming more difficult. Now, of course, this also depends on our own analysis. So the difference between left, so what you see in red, and the difference what you see in right, in blue, is our assumption on the spin. So how much is a neutron star able to spin? And depending on where you set your prior, so where you set your prior information, the results will vary somewhat. Not hugely, but somewhat. So that was the first kind of detection. This is the first example of what we can do. Now, if you project this to the future, again, this is a tidal deformability. And now if you look at, what if we don't have one measurement, but we are able to stack, many measurements? Assuming that all neutron stars behave the same, you can start stacking measurements. And you see here, you see 3 experiments where we have a hard equation of state, a moderate equation of state, and a soft equation of state. And the first measurement will give you very little information. But as you get to maybe 10, 20, you start to see a trend towards hopefully, the correct one. Now, of course, this is under the assumption that all neutron stars behave the same, and that everything you've measured was neutron stars, of course. That's still a hard thing to say, but the more detections we get, I think, we're starting to see more and more precision in the mass radius plane that we can constrain. Okay, so that was the in-spiral. And now we can again take a look at the post-merger, right? So I mentioned here that the post-merger signal for a neutron star, binary neutron star, is very different from a black hole. And so we can also take a look and see if we can just in isolation find the post-merger signal. So what you see here is the frequency, and here you see the square root of the power spectral density. So this is, here you see Ligo sensitivity. These are the LIGO, this is Virgo sensitivity, this is Geo sensitivity. And in the dots, here are the dots, these are some of the sensitivities that our analysis is able to reach. Again, this is not to, this is not to claim anything or say anything. And in fact, these results are very, uninformative. Other than we've performed the search here. This is the limit we're able to set on how much power was radiated in the post-merger. But so far, nothing substantial has been found. Now, in recent years, there's a lot of work going on in modeling these binary neutron stars. And in particular, how to really go to the closer and closer to the merger. And one of the developments I think that is very interesting is how to link the in-spiral, the first portion of the signal, to the latter portion of the signal, the post-merger part. Is there a way to predict or to model from the in-spiral on how the post-merger signal works? So here on the left, you can see this is frequency. Again, this is just amplitude. These are the post-merger signals for different equations of state, different models of neutron stars. And you'll see that they have different characteristic frequencies. It depends on the size and how well they're able to vibrate. And people have started to relate that to the in-spiral, to when these objects are still separated. And if you can do that, then there's a lot of gain to be had. So this is a figure where I'm showing, as a function of number of events, the what we call performance boost here. Here's just the improvement in the measurement of the tidal deformability that you can get if you can access also the post-merger information. Now, people shouldn't confuse this with, but you can't see the post-merger information, right? Because that's what I showed you. You can't, in isolation, see the post-merger information. But what you can do, of course, is even in the absence of post-merger information in a particular frequency, you can learn something. And this actually goes to show that even with one single event, having access to, closer and closer to the merger can gain you 60 all the way up to 100% of precision. So this is the important part, right? We need better models. We need more modeling on the binary neutron star side so that we can, really extract with confidence some of the nuclear physics that is going on. Okay, now one thing that one of my students has been playing with is asking the question, can we distinguish when you have a neutron star coalescence, can you distinguish whether it immediately collapses into a black hole or whether it remains in some hypermassive neutron star stage for at least a significant time? Significant, not that significant, but measurable amount of time before it collapses. Okay, and so assuming that you have a good enough model for the merger and the post-merger, then this is just, again, as a function of number of events. You can see that it's, we don't need that many events to be able to determine at which mass cutoff does this split happen, whether it falls into a black hole or whether it falls into a neutron star. Again, this is a rather toy model, but I want to highlight that we don't necessarily need that many events to be able to I think, look into interesting aspects of these mergers. But we do need very accurate models, or good models. And I think that's really where the gain can be had in the coming years. Okay, so this is the last section. And I want to just talk about cosmology. This is something I think most people here are familiar with. I'm not going to spend too much time on it. So one conventional way to do cosmology is just to trace the redshift and the luminosity distance, and then look at how your sources evolve over time. And then you can parameterize that, at least in the Friedmann-Robertson-Walker metric, just Hubble constant and some mass fractions. And so for gravitational waves, one of the, I think, usefulness of the measurement is that we can get the distance without needing some sort of cosmic distance ladder, right? And this is something that Ray explained, and I'll repeat kind of what he said, and that is, from the frequency evolution, we can get the mass. And we can also, therefore, say how much was the intrinsic luminosity. And so if you have the intrinsic luminosity and you measure the flux, you can say something about the luminosity distance at which this event occurred. And so that's one of the I think real contribution that gravitational waves can make. But of course, you run into the other problem, and that is, how do you determine the redshift? Now there are ways. I'm not going to discuss them in detail. It does require some modeling, but there's, to a certain extent, some redshift information to be gained. But if you have the two, you can start doing some cosmology. And so this is the Hubble constant measurement that Ray also showed. And so we see here, this is the Hubble constant, and this is the posterior density that we've measured. And in here, we took the gravitational wave measurement of the distance. We took the EM observation, or the host galaxy identification, to use that to get the redshift that way. And that leads to this rather broad detection. Now you may wonder, you may ask, why is this so broad? And that is, our distance measurement, even though it doesn't require a cosmic distance ladder, is still very uncertain. And that mainly has to do with the uncertainty of how the, well, there are two. There's where in the sky did it happen, and also how is the binary orientated with respect to us, if it's face on or edge on. And that's, largely the cause of this uncertainty. But nevertheless, just with our measurement of distance and with the host galaxy identification, we've arrived at a Hubble constant that is consistent with some of the other measurements, even though they are not consistent with each other. At least we're not adding to the problem. Okay, so that's the distance measurement. Now again, if you project this forward, if you go forward, then one of the things that you may be able to expect is that, again, with 10, 20, more and more sources, we will get better and better accuracy on the Hubble constant. And I think realistically, maybe the best that we can do is, tens of %. That's what I would say. But it will, it will be determined by the number of events that you'll be able to see. Now, if you go to third generation detector, that's when we can go for things like mass fraction, dark energy, dark matter, dark energy, and so on. But it really needs the third generation, both the sensitivity and also the number of sources. Right? To a certain extent, some of the gravitational wave things that I've shown is really a numbers game. You need more and more number of sources. Okay, so I come to the final part, and this is the part where I was supposed to talk about for 45 minutes, and now it's all condensed into the last 10 minutes. But I want to just close out just the lensing, just discussion on lensing. And this is just a setup that we're talking about, a gravitational wave source. You got LIGO, and you got some lens. I say galaxy lens here, any lens, doesn't matter. And so a year ago, actually, Tom Broadhurst, who is working with George on the paper that he just presented, asked me to do this calculation. He asked me, he says, what is the likelihood that we see lens signals? And so I did this calculation, just basically using some of the knowledge we have from the LIGO detectors. Okay, so including even the mass measurements are basically, I would say, conservative measurements that we did with the LIGO events. And everything else is very similar to what George said. And here I'm showing at least the rates that I calculated as a function of the SNR threshold. So depending on where you claim a detection, you'll see a different number of signals. And so in the solid line, you see the unlensed events, and in the dashed line, you see the lensed event. And I've left out some of the kind of intermediate kind of figures here, but the main crux of the story is if you just assume everything to be, I'd say, vanilla, then the ratio between lens and unlensed is about 1 in 100. Now, of course, as LIGO becomes more sensitive, you're going to push down the SNR threshold. This is assuming 0.1 sensitivity. But if you push down, if you make your detector more sensitive, that means that you're pushing your detector threshold to the left. And so if you scale it down with 3 towards design sensitivity, you're seeing we're in this situation here, where, of course, we're expecting hundreds of events with LIGO towards design sensitivity, but the factor of 1 in 100 means that there's a likelihood that you also see lens signal. And the error bars are mainly just the uncertainty on the local merger rate. Now, I made the plot very similar to what George has showed as well, but these are from my calculations that I did before. So this is the observed redshift and the detector frame chirp mass. And in color, you see the probability that it's lensed divided by the probability that it's unlensed. So in red, this is the regions where it's highly likely to be lensed. And when you go into the blue area, this is where the probability is very low. And I've took the liberty to plot all of the LIGO events here. Now, of course, I wasn't as bold as George, going in and really making the case for basically cutting off the mass function to do this. So we are working with a relatively broad mass function that is consistent with the LIGO detections that we have. But so if you assume that, if you take that, then this is the landscape of lensed signals in the redshift chirp mass signal. So you can see here, there's one here on the edge, and that's actually the LVT detection, the detection that you could barely make. Because if you look at this plane, this curve that you see here, this is the edge of detectability. So whatever SNR threshold you set, this is the edge. And this edge here, on the other hand, that's where the mass function cutoff happens. So in our case, we assume a power law mass function. And so the more you go this way, the less likely you'll see any sources. And so depending on where you cut off your mass function, how steep you let your mass function go down, you can bring this curve up or down. But this is the figure that I did a year ago, and if you just conservatively take what we know from LIGO, there doesn't seem to be any tension whether these signals need to be lensed. Now, I also promised in the discussion here during the break that this is the cumulative distribution for the time difference if you assume these are strongly lensed signals based on some galactic lenses. And so this is the cumulative probability. This is the time scale in seconds. And so what you'll see is that most of them, this here is a few months. And so what you see is you expect that most of the multiple signals happen within an observation run, but that very few of them overlap right on top of each other. Now, of course, that depends on the magnification as well. This is marginalized. So I've basically integrated out all of the possible magnification. Right? George showed that's 1 over mu cubed. But just, if you don't know the magnification, then this is the cumulative probability. And so there is a chance that within or in between observation runs, you may be able to see the auxiliary image or signal. Okay, now actually one thing that I find, if not even more interesting, is the prospect of diffraction. I think someone here should recognize this figure. And that is when you make the masses of your lens smaller and smaller and smaller, at some point you're going to go into the diffraction limit, the wave limit. And what happens is then you're getting a deformed signal. You're deforming your signal in a characteristic way. And this is just, the amplification function. This is just deformation. And what I'm showing here is the actual deformed signal. So in blue, you see the, I'd say, unlensed binary black hole signal. And in red is what you'll see if there is, a smallish mass in between you and the signal. And you'll see this characteristic bumping that goes on. And I think, we actually did the calculation. And this is using, fully using LIGO's infrastructure. And I'm just asking, to what precision can I measure the mass of the lens by considering these diffraction effects? And so you can see that the precision is maybe hundreds of solar mass wide. But it also means that if your mass is, let's say here around 400, it's just an example, then we actually have a way to observe an intermediate mass black hole through its diffraction effects. So if there's an intermediate mass black hole between you and the signal, then that is something that we will be able to pick up and say, there must have been something there. And we even did a comparison between just a point mass, where you assume it's a black hole, or more an extended lens of similar mass. And those two are distinguishable. I don't have the slide here. But for me, this is also another, I think, very exciting avenue for lensing. It's not necessarily the strongly lensed signal, because, and this was mentioned before, how do you identify, if they're separated in time and not necessarily overlapping? How do you identify them to be a lensed image? Why not just two images, right? And that's a statistics game that I think is maybe quite difficult to conclusively say that two detections were lensed images of each other. But whereas if you look at the diffraction effects, and this is even even including effects like spin and so on, we can still say to quite a good degree of accuracy that there was some lens in between us and the signal. So I think this is an interesting aspect as well. So I'll just leave here with a summary. I'm running out of time, but I'd be happy to take any questions you may have. Thank you.
So, all right, we have some time for discussions. Okay, sorry.
Can you mention a little bit more about the mass cutoff of post-merger signal?
Okay, sure. I mentioned this before as well. This is a little bit of a toy model. But what we did here is the following. We assume a binary neutral star. And so we either attach a post-merger signal with some equation of state, or our signal at the post-merger is the black hole ring down. Mm-hmm. And then we ask the question, can we distinguish one from the other?
I thought this is quite hard. We need something like very close event, like 20 megaparsec, 10 megaparsec, but you show here.
Right. So the thing, what we do is we actually assume that we know the full model. So not just the post-merger. If you just talk about the post-merger, you need it to be very close. Indeed.
So you use something like tidal deformability information and
yes. So you start off with knowing, so what the masses are, and then you look at, do I see a post-merger signal that is consistent with the masses I've measured before? And that actually gives you a lot of extra information, so that even with just a few events, again, this is a toy model. We assume that we know the model, but this is actually doable. And I think that is a shift where we need to go from, is not just looking the in-spiral and the post-merger in isolation. It really is the whole signal that can get you a lot of information.
Right, but it sounds like you have to know something, the relation between the tidal deformation and the
Sure.
maximum mass.
Yeah. So I mean, for this study, we used some phenomenological model that Sebastiano made. Again, I'm not touting that this is the end-all thing, but I hope to be able to convince people that if you have access, if you have enough simulations where you can really, to a good degree, model, not the whole spectrum, just where these peaks occur, based on the in-spiral, you can actually get a lot more information out.
Okay, thank you.
Let's move on.
For GW17, H17 case, the number of cycles around over the chap signal is 2000 and the duration is 74 seconds. Can you show me as the constraint of the post-Newtonian parameters?
So that one is still running. So we're actually still running that.
Because
Because it has so many cycles, the analysis is still ongoing.
Okay.
So we don't have these constraints yet. So I expect that they may be done in order of 2-3 months is when you can expect them, but they're still running. The problem here is, of course, we need to also take into account the tidal effects that are present as well. And so we're actually needing to control for those systematics before we can also study the post-Newtonian bounds.
Okay.
So that's a difficulty now.
We are waiting.
I'm working as fast as I can.
All right, let's
Sweet?
take the.
Sweet? Okay.
Yeah, please, you have the mic.
So in measurements of tidal deformability
Yeah.
in GW17, 0817,
Yeah.
How do you disentangle that from scalarization effects in alternative theories of gravity?
How do you disentangle that from?
So tidal
Sure.
deformability, as far as I know, is degenerate with some scalarization effects in scalar tensor theories of gravity.
Sure.
So so when you make a measurement of, say, the Love number, for example, do you take into account, isn't it possible that reflects, some kind of scalarization effect instead? And is this taken into account in the analysis?
If the one that I showed with just measuring the tidal deformability, no. So we don't here add any physics beyond GR. So it's just pure GR and then the tidal deformability effects on top of it. On the testing GR side, we are trying to put everything in there. But
Will it be possible to disentangle the two?
it's very difficult. These effects are already at high PN order. The tidal effects are to a certain extent measurable because the amplitude, so the effect is rather large. But for the scalarization and things, it depends on the coupling constants and so on. So I think it's just a game of chicken and egg at some point, whether these are tidal effects or whether scalarization effects beyond GR effects and so on. I don't expect that even now or even in the foreseeable future we'll have enough sensitivity to do that.
Okay, we still have 2 questions.
Okay.
Yeah, I think it's a bit too simplistic to suggest that LIGO will replace all binary pulsar tests because the data you've shown is 10 years old. And also I think we can see some things with pulsars that you can't see with LIGO, like light propagation effects. And we can probably get EOS straight from the binary pulsars without having tidal infrared deformation to take into account. So I think it's the beauty of it is the combination of the LIGO and the binary pulsar results.
Absolutely, and that's why if I did, then I apologize. I didn't mean to offend that or suggest that one replaces the other. I think it really is at a very different regime of strengths of GR effects, and so we have very limited ability to go.
We have precision. You have the higher orders, and I think the combination of both is very nice.
Very well. Yeah.
Okay, all right, let's. Okay. All right, so so let's join to thank Tjonnie for a nice talk, and also thank Roger